Everyone, today I'm going to be going over the distance modulus equation in astronomy. The equation is basically the difference in the apparent magnitude and the absolute magnitude is 5 times the log base 10 of the distance to the star minus 5. So basically it's the difference between the apparent and the absolute magnitude. So let me just I think let me redraw this because this is a small m minus big M, and the small m is the apparent magnitude, and the big M is the absolute magnitude of the star that you're observing, and the absolute magnitude is the observed magnitude that is of an observer 10 parsecs away, and then d is the distance in parsec. Okay. You might have also seen this equation in this form as just as d to the power of 10 over 5, and then this is on the power of 10. I should make that more clear, that this is 10 to the power of this value. And then this is basically a rearrangement of this equation because you're taking out the d and the log and solving for d. Okay, let's try a few practice problems with this equation now. Just take a second to post it. Okay, so a star has an apparent magnitude of -5 and an absolute magnitude of -26.3. How far away is the star? And give your answer in megaparsecs. So the apparent magnitude is -5. So if you just plug into the equation, it's -5 minus the absolute magnitude, which is -26.3. And then that's going to be equal to 5 times the log base 10 of d, which is the distance which you're solving for, minus 5. And we can just solve this, and -5 plus 26.3, and that's going to be equal to 21.3, and then that's equal to 5 log 10 of this d minus 5. And we can add 5 to both sides, so we get 26.3 to 5 log of d. And if we divide by 5, we get log of d equal to 5.26. And if we solve for d, we get a big number that's like around 181,970.08 parsecs, which is equal to 18.2 megaparsecs. So it's just basically plugging into this equation. So let's try another equation. Let's try another problem with this, with using distance modulus. Oh, and also before I forget to mention, it's this part of the equation, m minus m is called the distance modulus, and this whole equation is called the distance modulus equation. So m minus m, small m minus big M, which is the difference in apparent and absolute magnitudes, is the distance modulus. So we can use that fact to solve this question. Just make that bigger. So if a star's distance modulus is equal to 0, then how far away will the star be? So we know that the distance modulus is 0, so small m minus big M is equal to 0. And we know that this is also equal to 5 log of d minus 5. So 0 is equal to 5 log d minus 5. So if we add 5 to both sides, we get 5 is equal to 5 log d. So you get 1 is equal to log d. And that therefore implies that d is equal to 10 because it's in log base of 10. So distance to the star is 10 parsecs. So another way you can visualize this is that thinking of apparent and absolute magnitude. So if m minus m is equal to 0, then they'll be equal. The apparent and absolute magnitudes are equal. So that means, as I explained before, absolute magnitude is the observed magnitude 10 parsecs away from the star, but apparent magnitude is the observed magnitude from where you are right now, like in this case the Earth. So if they're equal, we must be 10 parsecs away from the object because the brightness, which is the apparent magnitude, will change on the based on the distance. So the distances have to be equal, and absolute magnitude is defined as being 10 parsecs away. So the answer is going to be 10 parsecs away, if you think about it that way. So let's try another practice problem. But we're now given the distance and the absolute magnitude, and we're asking to solve the apparent magnitude. The absolute magnitude of a star is negative 26. Solve for the apparent magnitude of the star if it was 30 parsecs away. So you can use the equation again. Apparent minus absolute is equal to 5 log d minus 5. And the absolute magnitude is 26, so m minus 26 to d minus 5. So m plus 26 here. So we can add 5 to both sides. So we get m plus 31. And let's not forget to plug in 30 for d. And then we get m plus 30. Oh wait, I think, yeah, sorry about that. I forgot to delete the negative 5 at the end. So m plus 31 equals to 5 log of 30. And we can simplify 5 log of 30 into, we know log of 30, if you plug that into our calculator, we get 1.477. And we can just solve for that. So 5 times 1.477 minus 31, and if we plug that in to our calculators, we get about negative 23.6 parsecs, which is the correct answer for the apparent magnitude of the star. And it should make intuitively a decent amount of sense because absolute magnitude is 10 parsecs away, and it's negative 26, and it'll be negative 23, and it should be greater if it was farther away. So that's the correct answer, and we can look at another problem right now, and it has to do with type 1a supernovae. Okay, type 1a supernova are caused when a white dwarf begins to accrete matter from a companion star. Once a white dwarf reaches 1.4 solar masses, it goes supernova. Because of how consistent they are, type 1a supernova are helpful in measuring distance to faraway galaxies. They have an absolute magnitude of negative 19.3. If a type 1a supernova was observed to have an apparent magnitude of 10.4, how far away is it in parsecs? So basically, the top few parts don't really matter to us, and the only parts that matter to us are the absolute magnitude and the apparent magnitude and what it's asking for. So basically, but it's important to know that they're standard candles and have like a fixed absolute magnitude of about negative 19.3. So that's pretty important to know. So we can just plug in the information that we know into the distance modulus. So the apparent magnitude is 10.4, and then um and the absolute magnitude is negative 19.3. So plus 19.3, that's equal to 5 log base 10 of the distance minus 5. So 10.4 plus 19 log 0.3, and that's going to be equal to 29.7, and that's equal to, let's just add the 5 here. That's equal to 5 log 10 of d. So this is going to be equal to 34.7, and that's 5 log d. Scroll down. So if we plug in 34.7 divided by 5 into our calculator, we will get something like 6.94. And then we know that the distance is going to be equal to 10 to the power of 6.94. And if we plug that into our calculator, we'll get something like 8709635. 9635.9 parsecs. And that seems to be the right answer. So